Hello everyone, and welcome to this video on gravitational potential energy. So start by formally defining gravitational potential energy, which is just the potential for the force of gravity to do work on an object. It is a type of mechanical energy, and it's energy that's stored between an object and the object's interaction with the Earth's gravitational field. I say the Earth because that's what we're typically going to use, but it could be the interaction between an object and any planet or star or moon's gravitational field. The symbol for all potential energies is the capital letter U, and then we apply the appropriate subscript. For gravity, it's going to be that lowercase g. Our units are joules, and the equation is the change in gravitational potential energy is equal to the mass of an object multiplied by the gravitational field multiplied by the change in the vertical position. So revisiting our list of mechanical energies, gravitational potential energy is another flavor of mechanical energy. So it does belong in this equation. EMEC equals the kinetic energy now plus gravitational potential plus any other forms that we introduce later on. So our equation for gravitational potential energy is pretty interesting because it's actually written as delta UG equals mg delta y. So it's the change in the gravitational potential energy. So what that really means is that this equation as written tells us the difference between gravitational potential energies between two different vertical positions or two different heights. So we're going to take a look at a couple examples where we use this equation and we look at some of the nuances of the delta UG and the delta Y. So the first problem is going to be pretty direct. We're just holding a block that's 2 kilograms 4 meters above the ground. We do release it and it falls to the ground, but we're not analyzing that in this problem. We just want to calculate the gravitational potential energy of the box Earth system with respect to the ground. So we're going to call the ground our zero height location. So this is where y equals 0. As the box is being held, it's at a position of y equals 4 meters. So the change in the potential energy from the ground with respect, or the ground to where the box is being held, is just going to be mg times delta y, and our delta y is just going to be 4. So we're going to go 2 times g, which is going to be 10 times 4. So we should get that the change in the gravitational potential energy from the ground to where it's being held is 80 joules. Now for our second example, we'll take a look at changing the height from that 4 meters to some other height that's not equal to 0 to make it a little bit more interesting. So we take that 2 kilogram block or box and we move it from that height of 4 meters and then we place it on a stool that's 1 meter above the ground. And we want to calculate the change in the gravitational potential energy. So we know that the box is starting at a position y initial equals 4 meters. And it's going to end at some final position yf equals 1 meter. So our delta y here is negative 3 meters. So we're going to use that as our delta y in the equation, and we'll just calculate delta ug is equal to 2 kilograms multiplied by the negative 3 meters multiplied by 10. So we're going to get the change in gravitational potential energy from where it's being held to being placed on the stool is negative 60 joules. Now we could do this problem another way where we just take a look at the potential energies with respect to the ground at both locations. So we see that the potential energy on the stool is just going to be 20 joules. The potential energy being held 4 meters above the ground was 80 joules. We've already calculated that, and this is with respect to the ground. So going from 80 to 20, we see that the change there is a negative 60 joules. And that's another way to do this type of problem. And that's going to be it on this introduction to gravitational potential energy. Thanks for tuning in, and I'll see you next time.